All right, so this one we've got chapter 6 and 6-1. And I think this is a pretty fun problem, actually. We're going to go through and look what it's asking for. It's essentially saying we have a 12-volt power supply, we have a resistor, we have an inductor, another resistor, and a capacitor. And what are the values of these actually? So we've got, the book says this is 3, and this is 4, and then this is L, and then this is VC. So there's a voltage drop over that. So essentially it's saying that this circuit's been on for a really long time at t equals 0. And all of a sudden at exactly t equals 0, we're going to flip this switch. And if we flip this switch, what's going to happen to our circuit? Well, essentially you're going to see that this is all one giant supernode to ground then. So this power is going to pump right through these this resistor to ground, and then this one's going to come through this resistor to ground. And then also it's going to say then at infinity, what's going to happen after we hold it for a long time, and this is going to slowly decay off and drain. You're going to see that, but this is still going to be able to pump out. So what it's asking is asking us to draw our circuits at all the way up to 0, negative infinity to 0, and then at 0, and then infinity. And then it's asking us to find our voltage across our capacitor at 0, our current through our inductor at 0, our current through our capacitor at 0, our voltage over our inductor at 0, and then our voltage across our capacitor at infinity, and our current through our capacitor at infinity. So let's solve these out right now. So let's start at t equals 0 from the minus side, from the negative side. I shouldn't put -1. T from the minus side. That's our first one. So this is going to be all the way up to 0. So all the way up to 0, let's just look at what happens. We have this. Our resistors are always going to stay the same. Our inductor, after a long period of time, this is just going to be a wire again. So we have our inductor, but it's just a wire. And then we're going to have nothing coming down because it doesn't exist. It's an open hole. So then we're going to have our resistor here. And then this is 4. And then we're going to have a hole here again because our capacitor is fully saturated. Because remember, after a very long period of time, this capacitor is going to saturate fully. And so what we have here, if you remember this, I'm going to take it even in pink. So at this point, we have from halfway through that power supply all the way over here, everything there is at a constant voltage. And if this is 12 volts power supply, any point on that end compared to here is going to be 12. So if you put an voltmeter anywhere in this, and you put one side anywhere up here and any other side down here ground, this whole thing is going to be 12 because there's no current flowing through. We have that pipe problem that we looked at way earlier where if there's a lot of potential pushing against this, there's 12 volts of push against this, but there's nowhere for that push to flow. And if there's no flow, you can't have current. If there's no current going across, the push is the constant everywhere. So it's like a pipe with water backed up in it. If I can't get some water out, I can't have flow. If I can't have flow, this is all backed up to 12. So the easy way to look at this is our VC. This is our voltage across our capacitor. Our voltage across our capacitor at 0 is going to equal our voltage across our capacitor at 0 minus 1, and that's going to equal 12 volts. There's 12 volts difference between these 2 points. Our inductor, our IL at 0, is going to equal, well, let's look, all the way our IL coming up to 0 from this side. This is just a short circuit, so that's also going to equal 0 current going through there, 0 current, because there's no current flowing through over here, so there's no current flowing through this. It's just a bunch of voltage holding together. So that draws out this one, and then we have our VC here, we have our IL here, we have our current through our capacitor here, because there's no current, so that's going to be 0. And then we have, well, let's step for the next one. Let's just draw the next one. T equals 0. So this is our next step. This is exactly at t equals 0. So that switch is going to go. So there's a slight difference between this, because up until this section, this has now been flipped. So exactly at 0, we have, whoop, oh, there goes my light lamp holder. Let's keep going. We have this as our circuit. And I'll explain it in a second. All right, so let's look at this. This is still going to be 3, and this is going to be 4. And this one, I'm just going to draw a little line there to keep it separate a little bit. All right. Okay. And this is 12 volts. And then this, positive, negative. All right, so let's look at what happens. So after all this period of time up here, this capacitor is charged up over here. Now, when we flip this switch right here to 0, this is going to short circuit this circuit. So this whole bit all the way up here is ground. Because look, it's just one giant supernode the whole way across. It's ground no matter where you go between those points. So that means that this is actually two different circuits. It's this circuit, so I'm just going to draw it one more time, equals, I'm going to draw this really simply, plus this. You see how this is two totally separate kind of circuits now because they both go to ground? I mean, it's like this ground is tied to this ground is tied, and that's the only difference between the two. So if we look over here, let's take this apart piece by piece. So the first bit, our power supply stays the same, our resistor stays the same. We've got our inductor now as an open in the circuit. Why is our inductor open? So if you think conceptually about inductors, what do? They resist change in current. So immediately we've changed our current here. And so our inductor at this point in time is going to be an open hole. There is no current passing through our inductor. And that makes sense too, because what do inductors do? If this is my inductor, let's just draw it. Yeah, let's just draw it here. As soon as I start pushing current through, all that current goes into starting to build these beautiful magnetic fields. And as these fields build, they require less and less current, so more and more current goes through, which is why at the long term, this field is totally built. Let's just say this can only hold two of these lines, so this is 100% saturated. If that's 100 saturated, then it's just a wire, and that's all it is, because all the current comes in, all the current comes out. It's not going anywhere. But if I stop, all of that field has to slowly decrease, because again, these resist change in motion, in current. So as I let go, now all this current starts draining off. But coming into this, all that current gets sucked up in this field, starting to make these field lines. And that's why, for the start, we've got this open circuit here. So that's why this is the first piece of this one. And what this is going to tell us, again, our VL, our voltage through the inductor at 0 equals 12. Because this is our voltage across. This is across a 9. See, here's their pipe the whole way again. There's 12 volts being pushed on this side, and this is ground. So between this is going to be 12 coming out. So that's the first half. Now we look at this. You notice this is not a capacitor anymore. I drew it as a power supply. Because in this top piece here, this capacitor has charged up. It's 12 volts, like I said, everywhere here. So this is 12 volts drop over this capacitor because this is fully saturated. When I switch this switch now all that capacitor is going to behave like a battery, and it's going to start discharging through this poor little resistor. And so because of that, we can start to look at some of the other implications. So this becomes a 12-volt power supply now. So if we want to draw this out, we're going to have our IC of Z equals 0 equals V equals IR, V equals IR. So this is going to be our IC equals minus 12 over 4. And so this is going to equal 3 amps. And it's minus because, again, we're going in the opposite direction as we were going before. So that's why we keep this minus in there. Or you can have, so again, I have an arrow coming down. That's kind of how I presumed it going down for the direction of current. If you have the arrow going up, you don't need the minus. So VL, our voltage of our inductor at 0, is going to be what? It's going to be 12 again, because it's just 12 in this node, and this is all ground down here. It's a giant supernode of ground. So those are our next two values. Let's cross that out. Okay, so now we're at t equals infinity. At t equals infinity, we've got a positive, a negative. We've got our resistor. We've got our inductor, which is going to be just a wire again. We've got a wire coming down. And then we've got a this, and then we've got again a hole in the circuit over here. So this is going to be 3, 4, and this is our VC of infinity. So look, this is what we've done for this last part. Again, if we go up to our original circuit, well, if we go to this one, the only difference between this and this is now the capacitor is fully saturated. I mean, it's fully discharged the whole way through, because remember, all this current is going to go around here. So this capacitor is going to discharge out and become an open circuit. So this VC equals 0. You could also have a line across here. Honestly, it really doesn't matter at this point if it's a line or if it's a hole, because it's going to be 0. There's no value there whatsoever. This is a little neater. So this is going to be 0. So the voltage drop across this and this is going to be 0, because again, this is all a node here. So the voltage drop over this resistor, again, 0. So it's like this part of the circuit in this case doesn't even exist, because all this power, all this current is going to go out through this. It's going to come through here and down. This is a short circuit because, again, it's an inductor. So over time, that inductor has filled up. This charge is filled. So now if I put 1 amp in, I get 1 amp out, because it's not going to store anywhere. It's just popping right out. And so this is completely going through. So my voltage across the capacitor at infinity equals 0, because it essentially is almost like it's not there. And then my current over the inductor at infinity is going to equal what? Well, let's look. This is just the circuit here. V equals I, whatever that is, R. So I is this. V is still 12 volts. So V equals 12 over 3 equals 4 amps. And that's 4 amps of current pumping out. 4 amps of current. And so that's how we determine IL. So again, that should cover all of these. IL at 0, VC at infinity, this one, this one, this one, this one, yes, and there's our 3 charts.
So I hope that helps to try to describe some of this of what's going on.
Let me know if you need more.